Greetings, welcome. I hope everyone had a very Merry Christmas, and now we can hope for a new year, and hope it turns out to be a good one, huh? There is actually so much to talk about and so much to go through that I sort of don't know where to begin. So I'm going to try to just focus in. And what we're doing is this Project Q, where we're looking at the Q factor of an LC tank circuit and how can we improve it. I think I was muttering something about that as you decrease pulse duration with a smaller cap, say, or with a smaller just constant DC pulse, the Q factor improves until it stops improving. And this would be another video, but I made a video on this. It was pretty boring, but I made a video on this. That the reason it improves up until a point is, I'm getting confusing. It's due to instantaneous amp flow. But you make more efficient use of your coulombs of charge with briefer and briefer pulse. That sort of trend is contingent upon your coil. And specifically, it's contingent upon the ratio of the induction over the resistance of the coil, or the tau time, how quickly the coil will charge to saturation. And why does it stop improving? You know, if you go to electronics tutorials and plug in the equation for instantaneous amp flow, it would improve in perpetuity. So why does it stop? It stops because the resistance changes with increasing frequency. Yeah, with negative resistance, you can see an oscillation that doesn't damp out. And you can ask AI about negative resistance oscillators, and it will tell you that. And you can also look up something like the Practical Oscillator Handbook. I'm blanking on the gentleman's German last name, but it's available online, I think legally and for free. But if you read between the lines, it's an oscillator of negative resistance oscillators. It's a handbook of negative resistance oscillators. The gentleman calls it the Handbook of Practical Oscillators, but he talks an awful lot about negative resistance there, and says some things very straightforwardly in terms of that they, continuously oscillate. And I haven't done anything with it, but he goes into detail about, this vacuum tube, this transistor, this circuit. And so I hope perhaps to get a chance to look at that. So as AI, Grok or GPT-4 or this Handbook of Practical Oscillators will tell you, there are oscillators that once you trigger them, they continue in perpetuity. And it's verboten to say it, but there's actually current, that's flowing then back and forth in perpetuity. And I believe current has an associated mass with it. The smallest unit of charge is the electron. So it's pretty much by definition a perpetual motion machine. But you're not supposed to say that. So let's try to focus in a little. Again, there's been so much I've been seeing recently to talk about, but it's not unaccepted conventionally that there are, for instance, negative resistance oscillators that continue to oscillate. So one of the reasons I'm doing this Q factor project is that, do you need a negative resistance element? And again, I haven't done anything with that yet. But do you need that? Or was Tesla, trying to say something when he labeled, one of his devices the amplifying transmitter? And that's a whole nother video. But when you break that down, it's an LC tank circuit in resonance going out to a secondary, and then using the earth as his capacitor. Crazy fuck. I know he meant well, but thank God he didn't get Wardenclyffe online. I think there are a number of ways it could have just destroyed humanity, but we have a number of those to worry about now. Sorry. So you have oscillations that can continue, and you have oscillations that can damp out. And without the introduction of negative resistance, can you have a situation where oscillations continue? Or is the best that the Q factor can become is, you know, like a Q factor of 1 million, which, you know, they see that. I mean, there are plenty of examples of that where it takes like 1 million oscillations before it goes down to 4% of its original amplitude. I don't know the answer to that, and that's one of the big reasons why I'm looking at this, but I, you know, have to wonder, and Tesla, you know, gave us so much of modern society still from like 100 years ago, that when he called it an amplifying transmitter, I think there was probably a good reason why he said that. So now to bring this back in, we have the idea of Q factor, like how undamped can we make an oscillation, and whether we will be able to make it just extremely undamped, or whether it can be something like with negative resistance where it continues to oscillate, or like the Don Smith stuff, the oscillation begins to grow over time. And I have no idea what's going to happen with any of it, but it will be fun to look at all of this. And even if you have an oscillation that becomes less and less damped, that's still a very useful thing to know. So now again, let's focus in, and there are a number of things. So we had said that it's the pulse time over the tau time of the coil, but the tau time of the coil changes as you increase the frequency because you get more reactive resistance, aka impedance. And there is a theoretical wing of that, wherein I will do videos discussing skin effect and proximity effect. Those are the two effects which alter your resistance dependent upon frequency. Second, I will do a video on, I don't know if I'll do any of these, but I hope to do a video on Wheeler's formulas for induction, because this is kind of a little bit down to the weeds, but important, because when you consider that the reactive resistance may be mitigated by changing the coil to mitigate skin effect and proximity effect, the question becomes, do you drop the induction so much of the coil that you would get no net benefit? In other words, if the changes that you need to make to mitigate skin effect and proximity effect drop the induction of the coil such that it has to go much, much faster, then you run into the same problem. But when you look at Wheeler's equations, you can see, and you can see it experimentally, that you can decrease proximity and skin effect such that resistance doesn't increase that appreciably without dramatically decreasing inductance. And that's like sort of the whole interplay, like, you know, where I think Tesla was saying, is there anything more interesting than LC tank circuits? At one point, I'd have to dig out the quote. It was something along those lines. But you can do that. It's an inverse square or a square function. So if you do that and you put, you look at it with Wheeler's equations, you lose maybe 20% of your induction, but you can now go 4 times as fast with frequency before you run into the same skin effect. So that's really cool. So, the other thing I've been working on assiduously is trying to 3D print a scaffolding to keep the wires a bit spaced from each other. And I'm working on that, I'm working on that. And it's actually a harder problem than I thought. I'll do a video on it. But in the meantime, I might just, until I do the video on skin and proximity effect, this might not make that much sense. But I have this big red coil, and to put it bluntly, proximity effect is generally more important than skin effect. And proximity effect, from what I've read, and again, I'll do a video on this where I'm discussing the papers, it increases exponentially with more layers. So if I can take that coil that you saw, that big red coil that was about 2 inches, and bring it down to 1 inch, that should have a higher Q factor. Now, that's not really where, it's not the end game, but it's probably worth doing because that'll take me like 3 hours to wind. Whereas what I want to do is I want to have each wire spaced, about 1 wire's length from the next one, and then I want to have the next layer on top of it, and I want to have that one offset 45 degrees from the first layer, and then the next layer and that one offset, and then the next layer and that one offset. That thing should rock. But I don't want to go there too quickly, just in case it doesn't work and it takes me like a week or 2 weeks to wind or something. I mean, I don't think it'll take that long, but between the printing and the talking, it might. All right, so I'm going to wrap this up except for one last thing, because I always feel like I should show something experimental, and that is that I bought an LCR meter, and I had an LCR meter. The reason I bought this one was because it said it was continuously adjustable for the test frequency. Now, what that means is, so for instance, if you have a big coil of wire, when you go from 100 hertz to 5,000 hertz, 5 kilohertz, at 5 kilohertz, there's going to be a lot of reactive resistance, aka impedance, aka skin effect, proximity effect. That's what causes impedance. Okay, we'll talk about that more later. But it would be nice to measure that. And I have one meter that I picked up years ago that it samples at 120 hertz and at 1 kilohertz. And I noticed that you can see on a coil that the resistance is different at the two frequencies because of impedance. So what it's actually measuring is your impedance. And that's so powerful. So I found this 1 meter out of China that says it's continuously variable at 1 hertz. You could 100, 101, all the way up to 100,000. Problem is, I can't get it to do anything other than the 5 or 6 presets. And so I've left them an email and said, why can't I do this? And please explain it to me. I'm so hoping they get back to me and explain it to me in a good way, and I'll put in a good word for this meter, because I can't tell you how powerful that would be. well, it's not that powerful, but it's just so dang cool. Because what you're really engineering for is the impedance and preserving as much of the induction as possible while keeping the impedance low. So hopefully they'll come through for me. They say they get back to you in one day, but I'll just show you a few different measurements on a couple different coils with that to wrap the video up. So thank you so much. There's going to be a lot more coming. Okay, so to sort of wrap the video up, I had this LCR meter and it tests at 2 different frequencies. So for Christmas I bought myself this meter out of China, East Tester ET433. And the reason I did so is because it was supposed to be able to test at any given frequency between 100 hertz and 100 kilohertz. I can't figure out how to make it do that. So let me at least show you what I have so far. So it's on the resistance. You know, you can change all that, of course, to capacitance and inductance, but we're on resistance. It's not showing the frequency, but the frequency is 100 hertz. So there we kind of see it. The frequency is 100 hertz, and it's measuring 5.5 ohms of resistance for the coil. And that's pretty much exactly what I measured with the multimeter, although it has less precision. So we can change the frequency, 120 hertz, same, 1 kilohertz, 8.6. Now when I had this meter hooked up, it was at 120 hertz or at 1 kilohertz. I was seeing about the exact same thing. So now we're at 8.5 hertz, and if I go to the next, it just jumps to 10, we're at 300 hertz. For some reason it starts to put a negative there, and we're at 18 kilohertz, and now we're at 64 kilohertz. So let's just think this through for a minute. If it were at, sorry that it's not showing up well, 1 kilohertz, and we have 8.5 ohms resistance, and then we go to 10, and we have 300. When we were back at 10 kilohertz, or 1 kilohertz, and we're at 10 now, 1 kilohertz, the resistance was around 10. Now it's 30 times greater, but we're only going 10 times as fast. So recall that the important thing is the ratio of the pulse duration over the tau time. The denominator of the tau time has increased 30-fold. Inductance has stayed the same, and your pulse has only gone 10 times as fast. So the Q factor is worse. Now, one of the neat things is it has a bunch of sub-menus. Equivalent series resistance, I take that just to be, I mean, it's the exact same number. I take this to be both of those, to be your impedance, and no, that's not it. That's not it. There it is. Q. There's your Q factor. Your Q factor is 19 here. And your Q factor, which is what this series is all about, huh? At 1 kilohertz, 1 kilohertz, the Q factor is now 67 with this
resistance having gone down to 8.5. So you can see as we're going faster, Q factor is going down. And that's exactly what was seen experimentally. I don't know why it puts a negative there, but we're at like 18 kilo ohms of resistance, and there 64. I don't know why the Q factor didn't go down more. Here we are at 100. Yeah, 10. And a good way to think about the Q factor is that's the number of oscillations till the thing is damped out to about 4%. I mean, that's a good approximation, about 4% of its original value. So there it takes 10 times 12, 67. Now we're moving the wrong way. And what I could do is do the same thing for this coil and this coil. This coil is actually 20 pounds of thicker wire. So you would think this one's better, but how much thicker it is, and it's not wound in a good circle. Proximity effect wrecks the heck out of this one. This one can go a lot faster because there's a lot less proximity effect, but I'll just give you another point here, is that the mass of wire is important. And so there's not enough mass of wire. And so this one, despite being wound better than this one, has a little bit lower Q factor than this one. All right, we'll wrap this up now, and we'll get back to it again soon. So stay healthy, and let's hope for a happy new year. Bye-bye.